It is time to start the last lecture of this session, and our one of the main organizers, Grigory Ryabov, and one of our regular participants, speaker of this workshop. So the floor is yours, please.
Thank you so much. Good afternoon. The title of my talk is Isomorphism Testing of Case-Spanning Tournaments is Fixed Parameter Tractable. And in fact, it is not about association scheme. But so the talk is based on joint work with Vikraman Arvind and Ilya Ponomarenko. So let's start with the definitions. And our first keynote notion is a notion of a fixed parameter tractable algorithm. Of course, we may speak about fixed parameter tractable algorithms for different purposes, but during this talk, we will discuss only graph isomorphism testing. And by this reason, we will speak further only about fixed parameter tractable algorithms for graph isomorphism testing. So, an algorithm for graph isomorphism testing is of fixed parameter tractable complexity, or briefly FPT algorithm, if it has running time of the form f of k multiple to the polynomial of n, where f is a function of the parameter k, but is independent of the input size, and n is the number of vertices of the input graph. So, despite of the fact that the term fixed parameter tractable was introduced not so long ago, FPT algorithms are of special interest in the context of graph isomorphism testing. And there are several such algorithms. For example, Evdokimov and Ponomarenko constructed an FPT algorithm for graph isomorphism testing, where the parameter is eigenvalue multiplicity of the input graphs. If I remember correctly, this paper was published more than 20 years ago, and it was written in another terms, but the constructed algorithm is exactly FPT algorithm. Arvind and his co-authors constructed an FPT algorithm for isomorphism testing of colored hypergraphs, and the parameter here is a color class size of the colored input hypergraphs. One more FPT algorithm was constructed by Lakshtanov and his co-authors for graph isomorphism testing, of course, and in their algorithm the parameter is a 3Vs. And we have a natural question here concerned maybe with the easiest parameter of the graph, namely with the maximal valence of vertex. Does an FPT algorithm for isomorphism testing for the maximal valency of a vertex exist? Such algorithm was mentioned in the paper of Babe and Lux in 1983, but the paper and preparation referred there was probably not published. And as we can check, to date, it is not known whether such algorithm exists. And maybe this is one of the main reasons to study this question and to do this work in general. So, our second keynote notion is a well-known notion of a tournament. I'm sure that everyone here knows what is it, but to make the talk self-contained, I will recall the definition. A tournament is a digraph obtained by assigning a direction for each edge in an undirected complete graph without loops. What is known about the isomorphism problem for tournaments? The isomorphism of tournaments can be tested in quasi-polynomial time. This was proved by Babe and Lux in 1983. But of course, this also follows from the recent outstanding Babe result about quasi-polynomial solution of the graph isomorphism problem. However, to date, no algorithms are known for isomorphism testing of tournaments which are FPT for some parameter. And this is another reason for studying this question and to be interested in this work. So let's move to colored diagraphs. I will provide some maybe very easy definitions, but only to establish our terminology on colored diagraphs. A diagraph is said to be colored if it is equipped with a linear ordered partition of the vertex and arc sets. The classes of the partition are vertex color classes and arc color classes. By an isomorphism between colored diagraphs, we mean an ordinary diagraph isomorphism that preserves vertex and arc color classes respecting the corresponding linear orders. So if you have an isomorphism between two colored diagraphs, must move the first color class of the first diagraph to the first color class of the second diagraph, so etc. It must preserve the linear ordering, and of course an automorphism of colored diagraph must preserve every arc color class and vertex color class. And now we introduce a new concept, but I think it is very natural because it generalizes the notion of a graph of bounded valency to the class of colored diagraphs. Generalizes in some sense. Of course, there are some ways how to do this, but we choose one of these ways. An arc-colored diagraph is said to be k-spanning for an integer k if the union of its arc color classes of maximal valency at most k is the arc set of a strongly connected diagraph. I recall that a diagraph is said to be strongly connected if for any vertex there is a directed path to any other vertex. So, and further, I will provide some examples of k-spanning colored diagraphs and even k-spanning colored tournaments, which imply, I hope, that this notion is not senseless and useless. And in fact, there are a lot of such diagraphs and even tournaments. So the first family of examples arise from Cayley graphs. Let G be a finite group and A an identity-free subset of G such that A contains exactly one element from G and inverse to G for every non-identity element G from G. The Cayley diagraph X over G with connection set A is a tournament. It is easy to check this because for every two vertices we have exactly one arc between them. Every partition of the set A, say A1, AM, induces an ordered partition of the arcs of X, where the I's class is the arc set of the Cayley diagraph over G with connection set AI, where I runs over from 1 to M. And the resultant colored tournament, say X prime, with arbitrarily chosen vertex colored classes, is k-spanning if and only if the union of all elements of the partition of size at most k is a generating set of G. In particular, if all elements of our partition are of size at most k, then our colored diagraph X prime will be a k-spanning Cayley tournament. And even for small k, the number of such k-spanning Cayley tournaments is exponential in the order of our group. So, in fact, we have exponentially many k-spanning colored tournaments, Cayley tournaments. So, let us consider the following family of examples of k-spanning tournaments. But before I recall one more definition, maybe it is well studied in the graph theory, but maybe in this context it is quite new and unusual. And tournament Y is immersed in a tournament X if the vertices of Y are mapped to distinct vertices of X, and the arcs of Y are mapped to directed paths, joining the corresponding pairs of vertices of X in such way that these paths are pairwise arc disjoint. So, and one more easy definition: a tournament is said to be transitive if the binary relation defined by its arcs is transitive. So, and now let us construct our examples of k-spanning tournaments. Let X be a tournament. Denote by k of X the maximal integer k, such that a transitive tournament with k vertices is immersed in X. Now, if we color our tournament X using the Westphaler-Lehmann algorithm, usual Westphaler-Lehmann algorithm, and we know that k of X is at most k, then we obtain a colored tournament, which is O large of k cubed spanning. This follows from the results of Lache. So once again, we take an arbitrary tournament with bounded parameter k of X, and we color this tournament using the usual Westphaler-Lehmann algorithm, obtained a colored tournament, and this tournament will be spanning for this parameter, O large of k. I would like to note here that the initial tournament X in general can be non-spanning. So for I mean the so I mean that yes, for any parameter. And maybe it should be mentioned here also that it is known fact that k of X is at least the logarithm of number of vertices of X. So, but maybe it is not quite important here, but so. And now let us formulate our main results. We prove the following theorem. Let k be an integer, then given k spanning colored tournaments X and Y, the set of all isomorphisms from X to Y can be found in time k to the power O large logarithm of k multiple to the polynomial of n, where n is the number of vertices in X. So in fact, we construct an FPT algorithm for isomorphism testing of k-spanning tournaments. Note that these results can be extended to a wider class of colored tournaments, for which the diagraph formed by the R-color classes of bounded valency is weakly connected, not strongly connected as in definition of k-spanning tournament, but is weakly connected, which means that for any two vertices of diagraph, there is an undirected path between these vertices. So, but to prove this maybe a bit stronger statement, we need more routine work, and maybe it is not so interesting. And by this reason, we prove exactly a theorem in this form. And one more observation: if k is equal to n, then the running time of our algorithm is quasi-polynomial as in Babay's algorithm. So this case is the worst. In fact, we derive theorem 1 from theorem 2. Let us formulate it. Again, let k be an integer, X a k-spanning color tournament with n vertices, and M the minimal size of a vertex color class of X. Then one can find the automorphism group of X in such time. Here we have the sum M to the power O large of logarithm of M. M is the minimal size of a vertex color class, plus K to the power O large of logarithm of K. K is a parameter of spanning multiple to the polynomial of N. N is the number of vertices. So, and maybe in the remaining time, I will provide some hints how we prove our results. At first, how we deduce theorem 1 from theorem 2. We prove the following lemma and use it to deduce theorem 1 from theorem 2. Given k-spanning color tournaments X and Y with n vertices, one can efficiently construct a set, say T, of X and Y of n colored tournaments, such that each tournament from T has 3n plus 1 vertices, is k-prime spanning, with k-prime is the maximal of 3 and k, and has a singleton vertex color class. And the set of all isomorphisms from X to Y can efficiently be found inside the union of automorphism groups of our tournaments from our set. Yeah. And maybe I will explain how we construct such tournaments, but maybe it would be better to do this using the picture instead of words and formulas. So I will try to explain the construction. So we have two tournaments X and Y, and we take two disjoint copies of X and a copy of Y, and we add a new vertex mu. Vertex color classes and arc color classes inside disjoint copies are the same as initial tournaments X and Y. But to construct a tournament, we need to add new arcs. So we add arcs from each vertex of X to the first copy of X to each vertex of Y, from each vertex of Y to each vertex of the second copy of X, and from each vertex of the second copy of X to each vertex of the first copy of X. And these arcs will be of the same color. So also we fix vertex alpha of X and vertex beta of Y. So, and of course, in the second copy of X, we have a copy of alpha. And what about arcs adjacent to new vertex mu? We add 3 arcs from mu to one copy of alpha, from mu to beta, and from mu to the second copy of alpha. And these 3 arcs will be of the same mu color. And one more arc color class is formed by the following arcs. From each vertex of the first copy of X except alpha to mu, from each vertex of Y except beta to mu, and from each vertex of the second copy of X except alpha to mu. And all these arcs will be of the same mu color. So we add 3 new arc color classes to obtain a tournament. And of course, a new vertex mu will be of the new color. So and we obtain exactly a tournament. And one of this tournament, but we fix a vertex alpha, and for each vertex beta, we construct in such way the corresponding tournament. And in such way, we obtain exactly n tournaments for each vertex of y. Vertex alpha is fixed. So, and for such family, we prove this lemma. So, and now how we compute the automorphism group. In fact, how we prove theorem 2. Maybe I restrict this theorem to case when m is equal to 1, when we have a singleton vertex color class. Because we apply this lemma exactly in this situation. But so let X be a k-spanning color tournament, and omega is the vertex set of X. And we have a singleton color class formed by a vertex alpha. So let us describe the following procedure. We put sigma is a set consisting of alpha, and K is a symmetric group of the set sigma. And while sigma is not equal to all vertex set omega, we do the following. Find vertex color classes delta inside sigma and gamma outside sigma, such that an intersection, say D, of delta times gamma with an arc with some arc color class of value set most K is non-empty. We always can do this because our tournament is k-spanning. So further, we construct an equivalence relation on delta in the following way. It consists of all pairs delta prime, such that the induced tournaments on the neighborhood of delta on D and on the neighborhood of delta prime on D are isomorphic. So if this equivalence relation has at least two classes, then we refine the coloring with respect to this equivalence relation using usual Westphalia-Lemon algorithm and stop the procedure. If not, then we find a solvable group L in some way, consisting the restriction of automorphism group of our tournament on color class gamma. And we put K to be equal K times L and sigma to be equal sigma union with gamma. So if our procedure stops at step 2.2, then the number of vertex color classes of X strictly increases and the automorphism group is preserved. So after at most n iterations of the procedure, we construct a solvable group K containing the automorphism group of our tournament X. And finally, the automorphism group of our tournament can be found in solvable group in polynomial time by the Baber-Lax algorithm. I think here we have two questions. Why it is important that we work with tournament? Why this does not work for arbitrary colored digraph? In fact, we use the following properties of tournament, that the automorphism group of a tournament is of odd order and hence it is solvable. And on step 2.3, it is important because if we deal with an arbitrary colored digraph, the constructed group K can be non-solvable, and this is a problem. So, and another question maybe here, why this algorithm is not polynomial time. On step 2.2, we construct equivalence relation E, but to construct this relation, we need to verify an isomorphism between tournaments with at most K vertices. And we use for this Barber-Relax algorithm, which is quasi-polynomial. And by this reason, we obtain exactly this time for the algorithm. And maybe one of the non-trivial steps here is, of course, finding of a solvable group L, because we use some risk products of permutation groups here. So, but maybe I will explain in private communications if somebody will be interested in this. So, thank you for your attention.
Okay, thank you very much for a very interesting talk. Any questions to Grigory? Well, I'm just wondering, is it possible to use your algorithm to be involved in gap? I mean, it looks like a procedure, right? Yeah.
Yes, I think it is possible to use it in gap, but I'm not sure that the time will be acceptable.
Oh, I see.
But I think the main problem for using it in gap here is construction of the group K,
right,
because we need to construct some special risk products or generalized risk products of permutation groups, and so it's I don't know how it can be translated into gap.
Yeah,
I think it's possible.
Yeah,
I think it's possible.
I see. Any other questions? If not, then let us thank Grigory again for this